Okay, let me go over this one more time. So we're going to let S be an oriented piecewise smooth surface that is bounded by a simple closed piecewise smooth boundary curve C with positive orientation, and let F be a vector field whose components have continuous partial derivatives on an open region in space containing S. Then we have this result that our line integral in space is equal to the surface integral. And so the surface integral, the curl of F, another way of saying that is the del operator cross F dotted with N ds over S. And so here you have sort of the situation. So you have your boundary curve C, and then that bounds the surface S, and then your normal is sticking up. So when it's sticking up, that means that that's going to induce counterclockwise orientation around your boundary curve. When the normal is sticking down, that induces clockwise orientation on the boundary curve. And so let's read this note here. The positive orientation on the surface induces a positive orientation on the boundary curve C. This means that if you walk along C with your head pointing up in the direction of the normal, then the surface will always be on your left. And so if you were walking along this and your head was pointing up, then the surface would be on the left. And so, so counterclockwise orientation, normal points up, clockwise orientation, normal points down. And so that is Stokes' theorem. And so we're going to look at a couple of examples, few examples today. All right, so this is our first example today. So we're going to use Stokes' theorem to compute the surface integral where F, the vector field is YZ, XZ, and XY. And S is the part of the sphere. X squared plus Y squared equals 4. That lies inside the cylinder. X squared plus Y squared equals 1, and above the XY plane. All right, so we're going to use Stokes' theorems to compute the curl of F dot N ds, where F is this vector field, and S is the part of the sphere X squared plus Y squared plus Z squared equals 4 that lies inside the cylinder X squared plus Y squared equals 1 and above the XY plane. So let's start out by graphing what the surface looks like. So we've got this sphere, and the radius of the sphere is 2. So there's a picture of my sphere. And then inside the sphere, we've got the cylinder. And then if we go up, and my sphere is not perfectly drawn here. That's a little bit better. And then we're just talking about this is my piece of surface right in here. So this is my surface S is right in there. And my boundary curve is right there. So this is my boundary curve C. And so because they're asking us to calculate the surface integral using Stoke's theorem, they're wanting us to use this formula. They're wanting us to use that the curl of F dot N ds is equal to the line integral over C of F dot dr. And so basically what they're asking us to do is calculate the surface integral using this line integral. And that would be to use Stoke's theorem. And so the problem is that I need to be able to write this boundary curve here. What's the formula for that boundary curve? So we need to find the boundary curve C. And so so what I'm going to do is I'm going to look at, I have the sphere, which is x squared plus y squared plus z squared equals 4. And then I also have the cylinder, which is x squared plus y squared equals 1. So in order to find this equation, I need to find the z. So it looks like it's going to be a circle that's right above the x squared plus y squared equals 1. But I need to see, well, what's the altitude of that circle? So if I plug in 1 for x squared plus y squared in the first equation, I'm going to get 1 plus z squared is equal to 4. And so that gives me z squared is equal to 3. And that implies that z is equal to plus or minus root 3. But because we want the part that's above the xy plane, we're going to take z equal to root 3. So we're going to take z equal to root 3. And so then c is going to be given by r of t. And so can anybody tell me the component functions of r of t? So it's right above this unit circle. So if we were to describe this one, we would have cosine of t, sine of t, and then the z component would be 0 if we were talking about this one. But in this case, we're up here at z equal to root 3. That's kind of like where that boundary curve lies. It lies in that horizontal plane. And so the z coordinate is going to be root 3. And then we're going to have t is in this range. And so this is my x, and this is my y, and this is my z. Now remember that my vector field is right here. So when I calculate this line integral, what this is really going to give me is the integral from 0 to 2 pi. And I'm going to have f of r of t dotted with r prime of t. That's what this is telling me to do. And so for my f of r of t, just to glance at we're going to have the yz, xz, and then xy. So this is going to give me So the y is z, remember that z is root 3 and y is sine. So this is going to give me root 3 sine t.
We can't see what you're doing, Professor.
And then xz is going to be cosine times root 3. So I'm going to have root 3 cosine t. And then xy, x is cosine, y is sine. So we're going to get cosine sine, which is the same thing as 1/2 sine of 2t. And then I'm going to dot this on with the derivative of my vector function, which is going to be minus sine. And then the derivative of sine is cosine. And then the derivative of root 3 is 0. And then dt. So we have that. So we're going to do that dot product. All right, so when we dot this, we're going to get minus root 3 times sine squared. And then we're going to get root 3 times cosine squared and then 0. So this is going to give me root 3. And then I'm going to have cosine squared of t minus sine squared of t. And remember that there's a trig identity with this one. So by this trig identity, this is going to be equal to the integral from 0 to 2 pi of cosine 2t. And then we can integrate that. So I'm going to have root 3 over 2 times sine of 2t. And so this is just going to give me root 3 over 2 times sine of 4 pi minus the sine of 0. And those are both 0. So it's just going to give me root 3 over 2 times 0 equal to 0. And so my question is there an easier way? In this particular instance. And so if we go back to our vector field, is this vector field a conservative vector field? Is this vector field a conservative vector field?
Yes.
What's the potential function? So if it's a conservative vector field, that means that there's a function of 3 variables whose gradient is this vector field. And so if f of x, y, z is if f of x, y, and z is equal to x times y times z, then the gradient of f would be equal to f, which in this case is yz, because the partial with respect to x is yz, and then xz, because the partial with respect to y is xz, and then xy, because the partial with respect to z is xy. And this implies that the curl of f is equal to what? So whenever you have a conservative vector field, what's the curl of that vector field going to be?
0.
The zero vector. Zero vector. So if we look at our surface integral, this is the same thing as the curl of f dotted with n ds over s, which is the same thing as the zero vector. And that is equal to 0. And so one thing to note, in general, if f is a conservative vector field, then the curl of f is always going to be equal to the zero vector, so that the surface integral, the curl of f ds, is always going to be equal to 0. And this should actually not be a surprise to you, because we already talked about that when you have a conservative vector field, the integral around any closed curve is always going to be equal to 0. That's a property of conservative vector fields. And when you're using Stoke's theorem here, when you're using Stoke's theorem, you're going to get a line integral. And so the line integral is equal to this, where this is a closed curve with some other conditions as well. And so we already knew that from before, that whenever you have a conservative vector field, the integral around any closed loop is going to be 0. And so since these two things are equal, then you're going to get 0 either way. But we also know it now because we know what the curl is, and we know that if we have a conservative vector field, then the curl is always going to be equal to 0. So that gives us a way of getting that. So sometimes you'll see a problem on a test or somewhere, and they're asking you to calculate a line integral, or you have to calculate that. And then if it's a conservative vector field, you already know that the curl is going to be the 0 vector. So this surface integral or the line integral will be 0. All right, so let's take a look at another problem today. All right, so we're going to evaluate this line integral when f is equal to minus y squared, x, and z squared. And c is the intersection of the plane y plus z equals 2 and the cylinder x squared plus y squared equals 1. And then we're going to orientate C counterclockwise when viewed from above. All right, so if we look at, so let's look at this curve here. And so here we're going to have, this is going to be your y-axis, and then here you're going to have your x-axis, and then here you have your surface, which is the y plus z equal to 2. And when viewed from above, we have this counterclockwise notation like that. So this is the x-axis. And so this is our curve here. And so what we want to do is we want to calculate this guy. Using this one. And I may actually calculate this both ways. So we could calculate this using either one. I think this one is going to be the easy one, but let's take a look and see what the calculation entails. And so if we're going to calculate it with this, we're going to have to calculate the curl. So let's calculate the curl of this vector field. So we calculate the curl. Remember, another way of writing that is it's the del crossed with F. And so if we put in the components of our vector field, we're going to have minus y squared x and z squared. All right, so let's see what we get here. So if we look at the first little part of it, we're going to have 0. The partial derivative of z squared with respect to y is 0. And then the partial derivative of x with respect to z is 0. So we're going to get 0. And then the partial derivative of negative y squared with respect to z is 0. And then minus the partial derivative of z squared with respect to x is 0. So the second component is 0. Now for the last component, we're going to get 1 minus a minus 2y. So it's going to end up being 1 plus 2y. So we have that. And then, so this is the curl of F. And then for the N is just going to be equal to, if we take this equation and we solve it for Z, we have that Z is equal to 2 minus Y. Now we could use any surface that has this boundary curve, but we have this nice surface that's handed to us. So, why would we take any other surface other than Z equal to 2 minus Y, this plane? So we use that. And then for this one, because our orientation on the boundary curve is going to be counterclockwise, we want our normal to point up like this. Our normal needs to point up so that we have that's going to induce this counterclockwise orientation on the boundary curve. And so for N, what we're going to do is we're going to take minus Zx minus Zy, and then 1 divided by the magnitude of all this, which is going to be just Zx squared plus Zy squared plus 1. All right, so when we calculate this out, the Zx is going to be 0. So we'll have 0. And then the Zy is minus 1. But then it's just a minus Zy, so this is going to be 1. And then this one is just a constant, it's 1. And we're going to divide it by the magnitude, which is root 2. Now remember that the ds is also going to be equal to Zx squared and then Zy squared plus 1 times dA. So in this case, we're going to get root 2 times dA. So when we're multiplying these guys, the root 2 is going to cancel, and then we're going to have this guy dotted with the curl. So what we're going to have is that our surface integral is going to be equal to our curl. And so our curl is the 0, 0, and the 1 plus 2y. And then we're going to dot this with 0, 1, 1 over root 2, and then root 2. We don't really need to write that because that cancels all the time. So we just have that. And then we're going to be integrating over d, where d is the projection of our surface on the xy plane. So in this case, our d is just going to be the disk, x squared plus y squared less than or equal to 1. All right, so we're going to be integrating over that. And so what this gives us is, when we do our dot product, we're just going to have the integral of 1 plus 2y dA over d. And since we have a nice polar region here, we're obviously going to use polar coordinates now. And so let's switch gears to polar. So in polar, we're integrating over this disk. So we have 0 to 1 and 0 to 2 pi. And the 1 plus 2y is going to become 1 plus 2 r sine theta. And then we're going to multiply that by the r d theta. So we just have to evaluate that. And so if we distribute that r, we're going to have the integral from 0 to 2 pi, and the integral from 0 to 1, we're going to get r plus 2r squared sine theta, dr d theta. And then we can, first of all, integrate with respect to r. We can't multiply them in this case because we're not able to factor this as a function of r times the function of theta. So we just have to do it the regular way. So we'll have the integral from 0 to 2 pi. I'm going to have 1/2 r squared plus 2/3 r cubed sine theta from 0 to 1. Everything's going to be 0 at the lower limit. And then if we put in the 1, we're going to have the integral from 0 to 2 pi of 1/2 plus 2/3 sine theta. All right, so we're going to end up with 1/2 theta minus 2/3. So this is going to be minus 2/3 cosine theta from 0 to 2 pi. And so what we'll end up with is 1/2 of 2 pi minus 0. And then minus 2/3 of 1 minus 1. And so we just end up with pi. All right, so we get an answer of pi. So let's see if we can work this the other way. So I think that this is the easier way, but let's see what you think. So let's go ahead and take this problem and we're going to rework it another way. So let's calculate the line integral of f dot dr directly. So we're going to calculate that directly. And so in order to do that, we need to somehow parameterize this curve. So we need to think, well, how could we describe that curve? So we know it lies directly over the unit circle. So we know that for C, we know that r of t, the x component is going to be cosine t, and then the y component is sine of t. But then we need to find a way to get the z component. We need to get the z component. Well, we know that z is equal to 2 minus y, because it has to be, this curve lies in this plane, directly above the unit circle. So what's the z component of my vector function going to be? So this is x, and this is y. And so what's the z going to be? Z is
2 minus sine t.
Yeah, 2 minus sine t, thank you. And then we're going to have the t going from 0 to 2 pi. Now, we also have to calculate the derivative of this. So we're going to have r prime of t is going to be equal to minus the sine of t. And then we're going to have cosine of t. And this is going to be 2 minus cosine t. Now remember that our vector field, our f of r of t, remember that our vector field is minus y squared, and then x, and then z squared. So what I need to do to calculate f of r of t is I'm going to have to put in these values for x, y, and z into this vector field. So what I'm going to get here is I'm going to have minus sine squared. That's the minus y squared. And then the x is going to be cosine t. And then the z squared is going to be 2 minus sine t squared. And so this is going to be my f of r of t. All right, so now what we need to do is we need to calculate our dot product. So then if we calculate the integral along C of f dot dr, this is going to be equal to the integral from 0 to 2 pi. And then we're going to have the f of r of t dotted with r prime of t dt. And so we're going to have the minus the sine squared cosine of t, and then 2 minus sine t squared. And then we're going to dot this with the derivative, which is going to be the minus sine t cosine t, and then 2 minus cosine t. So we have all that. And so we need to do this calculation here. So what I'm going to get when I multiply this out, I'm going to have sine cubed plus cosine squared. And then I'm going to have 2 minus, I'm going to have minus, and then 2 minus sine t squared times cosine t. And all of that I'm integrating with respect to t from 0 to 2 pi. So I have that. And so then to help me integrate this, I can write the first part as, I can write this as sine of t times 1 minus cosine squared. And so what I'm going to have is I'll have sine of t minus cosine squared of t sine of t. And then the cosine squared, I can write that as 1/2 plus 1/2 cosine of 2t. And then this last part, let me just double check this here. Oh, this 2 is not there, sorry. When I took the derivative, the 2 is 0. That's my mistake there. So this should be that should be gone. So when you're multiplying, you're just multiplying it by negative cosine. So here you just have that. So this is right here. And so we're going to have just minus so I'm just going to have minus and then 2 minus the sine of t squared times cosine t dt. So I have all that. So when I integrate this, I'm going to have minus cosine t, and then plus 1/3 cosine cubed of t, plus 1/2 t, plus 1/4 cosine 4t, cosine 2t. And then for this last part, I'm going to have minus and then 2 minus the sine of t cubed all over 3 should be plus from 0 to 2 pi. Because when I take the derivative of the inside, I'm going to get that the derivative of the inside is going to be minus cosine, and I have the minus and the cosine there. All right, so let's see what we get here. So we're going to have, for the first part, we're going to have minus 1 times cosine of 2 pi minus cosine of 0, which is 1 minus 1. And then here we're going to have 1/3 of 1 minus 1. So these first ones are going to be 0. Then I'm going to have 1/2. I'm going to have 2 pi minus 0. And then I'm going to have 1/4 of 1 minus 1, which is 0. And for the last one, I'm going to get 1/3. And I'm going to have, when I put in the 2 pi, I just get 0. So I'm going to have 1/3 of 8 minus 8, which is 0. So all in all, I just get pi. But I think you would agree that the first way would be easier than the second way. What do you think?
Agreed.
Okay, thank you so much. All right, so let's take a look at one more problem with Stokes' theorem. And so we're going to use Stokes' theorem to evaluate when f is equal to 2z, 4x, and 5y. Those are the component functions. And c is the intersection of the plane z equals x plus 4, and the cylinder x squared plus y squared equals 4, with counterclockwise orientation viewed from above. All right, so there's the problem. So we're going to use Stokes' theorem to evaluate this line integral. So that means we're going to use the surface integral to evaluate the line integral. And C is F is the vector field. The x component function is 2z. The y component function is 4x. And the z component function is 5y. And C is the intersection of the plane, z equals x plus 4. And the cylinder, x squared plus y squared equals 4, having counterclockwise orientation when viewed from above. And so a lot of times people think, oh, Stokes' theorem is too hard. I'm just going to forget about any problem that says Stokes' theorem. But actually, when you look at this problem, it's going to be very quick to do this problem. So what we're talking about is we've got the cylinder. So we have a cylinder of radius 2. And so in this case, we're going to have, this is going to be the x-axis. And then here you're going to have the y-axis here. There's the y-axis right there. And here you have this z equal to x plus 4. And then you have this counterclockwise orientation when viewed from above, which means that my normal has to go up like this. So that way, when you have this counterclockwise orientation, the normal points up. All right, so in this case, my surface is going to lie over, we have the x squared plus y squared equals 4. So my projection onto the xy plane is just x squared plus y squared is less than or equal to 4. So we know that this line integral is equal to the surface integral. So we're going to have to calculate the curl of f dotted with n ds. So that means I need to calculate the curl of this vector field. So if we calculate the curl, remember that's the del cross f. So we're going to have the I, j, k, and we'll have the partials. And then we'll put the component functions in there, the 2z, the 4x, and then the 5y. All right, so the first one is going to be 5 minus 0. So we're going to have 5. And then we're going to have 2 minus 0 is 2. And then the last one is going to be 4 minus 0 is 4. That's my curl. And then for my n, so my n is just going to be equal to the zx and zy with a minus, and then 1 divided by the magnitude. And so this is our z. So this is just going to be equal to minus 1, 0, and then 1 divided by root 2. And so remember that the root 2 is going to cancel. So what this means is that if I look at the curl of f dotted with n ds over s, this is just going to be equal to, after we cancel those root 2's, we're just going to have the 5, 2, 4, and then we're going to dot this with minus 1, 0, 1, dA, after we cancel those over d. And so when we do this dot product, we're just going to get 5, negative 5, plus 0, plus 4 is negative 1. And so we're going to have and so what's the next step here? So I guess we could convert to polar, but this is just going to be equal to the area of D. Area of D is an area inside of a circle. So we know that. So it's going to be negative 1 and times the area of D, which is negative 1 times pi times 2 squared. And so that's equal to negative 4 pi. If you want to, you can convert to polar also. But you can see this problem is not difficult at all. It's pretty straightforward. And so not every problem involving Stokes theorem is going to be too hard. A lot of times the Stokes theorem is kind of like a shortcut, just like the Green's theorem was. All right, so what I would like to do is to put some of the pieces together that we've been talking about in this class. And so we're going to be putting pieces together. Meaning various concepts that we've been talking about, we're going to see how they're related to each other with the theory that we have. And so the first thing we're going to look at is that Green's theorem is a special case of Stokes' theorem. All right, so we want to see why is that true. So remember I've told you before that you can think of like Stokes' theorem as like a higher dimensional version of Stokes' theorem is a higher dimensional version of Green's theorem. So we can think of, remember that Green's theorem was this. What Green's theorem said was that if we had Green's theorem was this. So if we had a closed curve, then we said that this could be written as a double integral over R of Qx minus Py dA, where, you know, maybe your R could be like that, right? And then you had your C was like this. This was your boundary curve. And so that was the Green's theorem. And so remember that this is the same thing as this vector field PQ dot dr. It's just another way of writing that as opposed to the differential form. All right, so okay, so we can think of F equal to P of xy, Q of xy in the plane as F equal to P of xy, Q of xy, and just make the third component function 0 in space. Also, if R is a region in the xy plane, we can think of R as a flat surface. with unit normal n equal to 0, 0, 1, which is equal to just the k. And so let's suppose that C is the boundary curve of R with counterclockwise orientation. All right, so then if we take the curl, of F, so we're going to have the I, the J, and the K, and then our partials. And then we're going to have the P and the Q and then the 0, like that. All right, so let's see what we get here. So we're going to get 0. We're just going to get minus QZ. And then we're going to get the PZ minus 0. And then for the last one, we're going to get QX minus PY. So we have that. And so then by Stokes' theorem, we have the line integral around C of F dot dr is going to be equal to the curl of F dotted with N ds, but that's just going to be equal to our integral over R of minus QX PZ, and then we'll have the QX minus PY, and then we're going to dot this with 0, 0, 1 dA. And so when you do the dot product, the minus QX is going to be multiplied by 0, the PZ is multiplied by 0. And so what we get is that we're going to get just the integral over R of QX minus PY dA, which is which is Green's theorem. Which is the result of Green's theorem. And so you can see that the Green's theorem really just falls out as a special case of Stokes' theorem. Any questions on that? Just the flat surface there. All right, so another thing that I promised you before, I don't know if you remember, the conservative test. So I mentioned to you before that once we have Stokes' theorem, we can prove the conservative test in space. And so let's see how that goes. So this is the conservative test in space. All right, so remember the conservative test. So we're going to, let me remind you of what the conservative test was. So we're going to suppose F is equal to, we're going to have P, Q, and R. And F has continuous partials. Have continuous partials on an open region D in space. Then if Py is equal to Qx and Pz is equal to Rx and Qz is equal to Ry on D, then F is a conservative vector field. So in other words, there's a potential function whose gradient is equal to this vector field on D. All right, and so here's how we're going to do this. So we're going to let C, so we'll do a little proof of this. So we're going to let C be a simple path in D. And so remember, that means that it's a piecewise smooth curve. So it'll be a simple path, simple closed path in D. So remember that one equivalent to a vector field being conservative is that it was independent of path, and independent of path was equivalent to the integral around any closed curve. The line integral was 0. So we're going to let C be a simple closed path in D. Then here's the tricky part. So then there is an orientable piecewise smooth surface S that's a subset of D whose boundary is C. And this is a true statement. It's not easy to show at all. So just to give you an idea of what we're talking about here. Let's say the curve is like this. It's piecewise smooth. And let's say the pieces are just line segments. And these are some line segments in space. Then what we could do to get the piecewise smooth surface is just take a plane that goes through each of the line segments. So we could have like a plane like here, and then a plane that goes through that other line segment, and then followed by another plane, and then another plane, and another plane. And so all these planes together give you a piecewise smooth surface with this boundary curve that has these line segments. Now, in general, it's not going to be this simple because let's say your segments aren't lines. Let's say they're curves. And so then you're not going to be able to have something as simple as just a plane that's going to have that, because this plane would touch these endpoints, but it wouldn't work for the whole curve. And so in general, it's going to be more complicated than for line segments, but you can see that what the idea is. And so you'd have to have like some surface that had this boundary curve, and then another surface maybe that would have, you know, another boundary curve that might look like that, and so on. Maybe, you know, this other one would go in like that, and then you'd have some surface that has that boundary curve. And so the claim is not easy to prove, but it's nevertheless true. All right, so then what we would have is that then the integral around C of f dot dr would be equal to by Stokes' theorem, the curl of f dot ds. But if we look at the curl of f, what this is going to be is we're going to have the ry minus qz, and then you're going to have pz minus rx, and then you're going to have qx minus py dot ds over s. And if you don't believe me, you could do your determinant. You'd see that it comes out to be that. But remember, we're assuming that pz is equal to rx. So in this case, this is going to be 0. And we're also going to have qz is equal to ry, so this is 0. And then qx is equal to py, so this is 0. So this is just going to be equal to a dot product with the 0 vector. And so this is just going to be equal to the integral of 0, which is equal to 0. So we're not quite done yet, though. So a curve C that is not simple can be broken up into a number of simple closed curves. C1, C2, all the way to Cn, with C equal to C1 union C2 union Cn. And so in this case, if we look at the line integral of C of f dot dr, this would be equal to the line integral over C1 of f dot dr plus the line integral along C2 of f dot dr, and then plus the line integral along Cn of f dot dr. And this is just going to be equal to 0 plus 0 plus 0 equal to 0 by the above. So what this means is that the line integral along C of f dot dr is equal to 0 for any closed path, whether it's simple or not, for any closed path in D. And that's equivalent to f is independent of path on D. And that's going to be equivalent to f is conservative on D. All right, and so that's why we have the conservative test in space, why that works. All right, so the last thing I want to do is I want to go over something called circulation density and see what this has to do with Stokes' theorem. All right, so we're going to talk about circulation density. So suppose D of A is a small disk of radius A centered at P sub 0 in space with boundary curve C sub A. Then if we look at this line integral of f dot T ds, C over CA, this is what's known as the circulation of F around C of A, which can measure the tendency for a fluid to flow in the positive direction around C of A. All right, so now suppose that F is a vector field whose components are continuous. Then the curl of F is continuous on D of A. And so if A is greater than 0 is small, the curl of F is going to be approximately equal to the curl of F at P sub 0, where P sub 0 is the center of that disk. And that's just because the curl is continuous. And so if the disk is real small, then the curl will not change that much on this disk. You would say that it's approximately equal to that. And so by Stokes' theorem, what we'd say is that f dot T ds is going to be the curl of f dot n ds. Now, what we can say is that the curl of f is approximately equal to the curl of f at P sub 0. And then n is constant because the normal to a flat plate is going to stay the same. It's not going to, if we have the normal to a flat plate is going to stay like that. So it's going to be like that. If you have a normal to a surface that's not flat, then on different parts, it's going to be different. But when you have a flat plate, it's always a constant, right? And so we can take this constant out. And so we can say it's approximately to that. And then we're taking the integral of 1 ds over dA. And what that would be equal to is it's going to be equal to the curl of F at P sub 0 dotted with n times the area of my disk, times the area of that surface. And so what we can say then we can say that this line integral is approximately equal to the curl of f at p sub 0 dot n times the area of the disk. And so if we divide through by the area of the disk, we have the curl of f at p sub 0 dot n is approximately equal to 1 over the area of the disk times this integral. And so this integral is called, the whole thing on the right-hand side is called the circulation density of f around c sub a. And the approximation gets better as a goes to 0 through positive values. And the curl of f at p sub 0 dotted with n would actually be equal to that limit. And so what we say is that the curl of f at p sub 0 dot n is the circulation density at p sub 0. And so the circulation density times the area of the disk is approximately equal to the circulation around the disk when the area of the disk is small. And so the circulation density at p sub 0, which is the curl of f dot n, will have its maximum when n has the same direction as the curl vector of f at p sub 0. Thus, the maximum circulation occurs around small disks with center at p sub 0 that are normal to the curl of f at p sub 0. Hence, if a small paddle wheel is immersed in fluid with the pivot at p sub 0, then the paddle wheel will rotate most rapidly when the spindle is aligned with the curl vector. So let's say we had this small paddle wheel here. So look at this paddle wheel here. And then you see you have this small paddle wheel and then its spindle is pointing up, but the curl vector is over here. So you see this direction. That means, like, if you're thinking about fluid flow, that means that fluid is flowing around that curl vector like that. So you can see if the fluid, and then that fluid is flowing like that right there at that pivot, like right there. And so these paddle wheels will catch some of that rotation, but they're going to get a maximum, they'll catch a maximum amount of that rotation if we take this spindle and we align it with the curl vector. And then what's going to happen is that those paddle wheels are going to be going like that, and then they'll catch that rotation around the maximum rotation, and that will make the paddle wheel rotate most rapidly. So here maybe it's going to rotate a little bit. So the rotation in the current is like that, and so it'll make it rotate a little bit, but not as quickly if it's aligned with as when it's aligned with that curl vector, because then those paddle wheels will catch all of that rotation in the current. All right, so what we want to do is we want to generalize this idea. So more generally, suppose S is an orientable surface with continuous normal on S, and F is a vector field that has continuous partials on an open region that contains S. So we can divide S into m times n patches, Sij, with piecewise smooth boundary curves, Cij, and area of each piece is going to be delta Sij. And we're assuming that it has small area. Also, we're going to let Sij bar be something in the Sij patch. Then if we take the curl of f dot n, that's going to be continuous. So the curl of f is continuous and n is continuous. So the dot product is going to be continuous on this patch. And since delta S sub j is small, what we can say is that the curl of f dot n is going to be approximately equal to the curl vector at that point, dotted with the normal at that point on S sub j. And so, so we're kind of generalizing what we did before. And so if we look at the circulation around this boundary curve, it's going to be equal to this by Stoke's theorem. And it's approximately equal to this because the curl of f dot n is approximately equal to this guy on Sij, so we can pull out that constant. And so this would be equal to the curl of F at Sij bar dotted with the normal at Sij bar multiplied by the area of that patch of surface. And so thus again, we see that the circulation density times the small area of the region is approximately equal to the circulation around the boundary of the region. So what this means is that if we have a small region like this, whether it's a circle or some other rectangle or some other patch, then the circulation around the boundary, maybe the tendency for fluid particles to flow around the boundary is approximately equal to the curl dotted with the normal times the area of the patch. And so that's why we think of the curl dotted with the normal as the circulation density. If we multiply the circulation density times area, it gives you approximately equal to the circulation around the boundary curve. All right, so we use Stokes' theorem to derive this, but you could also observe that from observing physical quantities out in nature. And so once we have that, we can kind of see why Stokes' theorem works. So this is going to be the basic idea of Stokes' theorem. Okay, this is Stokes' theorem, that this line integral is equal, the circulation on the boundary is basically the sum of the circulation on the surface. So we're going to divide S into M times N patches, Sij, with piecewise smooth boundary curves, Cij, and S sub ij bar is going to be a point in the ijth patch. Then the circulation density at Sij is going to be the curl of F at Sij bar dotted with N at Sij bar. And what we can say is that the circulation density times the area of the patch, which we're going to call delta S sub ij, is approximately equal to the circulation around the patch on the boundary curve. And this approximation is going to get, if the patch is small, and that approximation will get better as the patch size shrinks. And one thing to note here is that the magnitude of the circulation density at Sij will be determined by the magnitude of the curl vector at the point and how closely the curl vector is aligned with the normal. So if these guys are the same, then that will increase the magnitude that we get. Because remember, it's defined to be a dot product, and we know about the dot product and how it's going to be equal to the magnitude of one times the magnitude of the other times the cosine of the angle between those, which will be a maximum when that angle is 0. All right, so for each of these boundary curves, we have this is approximately equal to the curl density times the area of the patch. So the circulation around the patch is approximately equal to the curl density times the area of the patch. And the approximation gets better as M and N get larger and delta S sub j gets smaller. The area of the patch gets smaller. So then what we can say is that the curl, if we add up over the entire surface, like here, this is going to be approximately equal to adding up all those line integrals over those boundary curves. But what happens if we look closely at that, so along each of these patches, we have a counterclockwise orientation. But what happens on this part? We can break this up into, we can break up the curve over this patch into 4 separate components, line integrals. And once we break it up into all the separate components, we see that the line integral over these parts cancel because we have the same segment and they have opposite orientation. So we have cancellation here, cancellation on these parts, cancellation on these parts, because you can have another one going here like that. Cancellation there, cancellation there, cancellation here, cancellation here. Gosh, so much stuff cancels. The only thing that doesn't cancel are these segments along the boundary. And so what happens is that this guy just becomes the line integral along the boundary, since the integrals along the inside edges will cancel after opposite orientation pairing. And so what happens is that this sum of all these line integrals just reduces to the line integral around the boundary, because all these opposite orientation inner edges are going to cancel. And so taking the limit as m and n goes to infinity, so this is the approximation here, and that approximation gets better and better. This is always true because they'll always cancel. And so what that gives you is the result of Stokes' theorem right here when we take the limit. All right, so I want to just show you an example. So in the last, let me see if I can zoom out here a little bit. So in the last video that we looked at the surface integral. I think this is the first example. We looked at using Stokes' theorem, and we had this surface where we were looking at the paraboloid 4 minus x squared minus y squared. And at the end, I showed you that you would get the same as if you changed the surface to the top half of the sphere, because the boundary curve is the same. So the boundary curve is going to be x squared plus y squared equals 4 in either case. So now that we kind of have a better understanding of Stokes' theorem, we can see why. So let's say we take this first surface, and so let's say we start breaking it up into patches. So I'm not going to do patches over the whole thing, but let's say we start to do that. And each patch has a counterclockwise orientation here. So we have these big patches here. So look what happens on these inner edges. So when we break this up, the line integral over this one will cancel with this line integral on this one going down, because they have opposite orientation. The line integral over this segment will cancel with this other one going up. If we come up over here, this line integral on this part will cancel with this other line integral up here, and so on. We'll have, these guys will cancel. These ones will cancel. These ones will cancel. So the only thing, so all cancel on inner edges. And the ones that don't cancel will be the ones on the boundary curve. And so after we split it up, so we can write the curl of F is going to be approximately equal to the curl density times, I forgot to write something here. This is the delta Sij. And each of these curl density times this area is approximately equal to the circulation around these guys. But you can see that what's going to happen is that everything's going to cancel, and we're going to be left with the circulation just along the boundary curve here. Everything else will cancel out. Now, let's say we had this other surface with the same boundary curve. Well, it's going to work exactly the same way. On these inner edges, they're all going to cancel. So all these opposite orientation inner edges, we're going to cancel when we're calculating this guy. And what we're going to be left with is just the line integral along the boundary. And so for that reason, the curl of f dot n ds over S1 is going to be exactly the same as the curl of f dot n over S2, even though the surfaces look vastly different because their boundary curves are the same. And so therefore, both of them are equal to this line integral. And so they're going to have the same value. This was S ij. All right, so now this is kind of, so you're ending Calc 3, so it's sort of like you're graduating from calculus at this point. So I feel like we should have some kind of celebration, or at least maybe kind of summarize some things that you may have not thought about that are kind of common to all the topics that you've talked about. So remember in Calc 1, you talked about the fundamental theorem of calculus. And so what that said is that if you had the integral of f prime of x dx, that is equal to f of b minus f of a. And one thing you want to note is that a and b are the boundary of the interval from a to b, which is the interval you're integrating over. All right, so some time went by, and then more recently we looked at the fundamental theorem for line integrals. And so what this says is that if we're integrating a gradient over c, the line integral, then this is equal to f of r of b minus f of r of a, where we're integrating over this curve. And so note the boundary of the curve c is r of a and r of b. Then we had Green's theorem. So Green theorems, again, we're having derivatives. Remember that the gradient is kind of like a derivative, right? You have the vector with fx and fy, that's kind of a derivative. So here we have derivatives, the qx minus py, those are derivatives. And what we have is that c is the boundary of R. And then this gives us the double integral over R. So when we integrate the derivatives over R, this gives us this line integral over the boundary of R. So now let's Stokes' theorem. Stokes' theorem, we have the surface, and C is the boundary curve. So here we have the curl that has derivatives in it, dot n, and that's equal to the line integral over the boundary curve. And then we have the divergence theorem. So the divergence theorem, S is a surface that's the boundary of the solid G. And then we have the divergence of F, there's certainly derivatives in that, over G is equal to the curl of F dot n over the boundary, which is S. So with the one thing that you can kind of take, the principle from all of this is that the value of a function on the boundary of a region determines the cumulative iterated effect of derivatives throughout the region. And that's kind of what's common to all these things that we've looked at in calculus. All right, so I just wanted to take the time to review a few examples. From this chapter. All right, so we're going to use the conservative test. is a conservative vector field on D equal to R cross R, and then find a potential function and use the fundamental theorem of line integrals to evaluate the integral along C of f dot dr when C is given by R of t equal to root t and then 1 plus t cubed. So we have that. So it says that this is a conservative vector field. So we have f is equal to x cubed y to the fourth, and then we have x to the fourth y cubed. So if we call this m and this n, we want to check is my equal to nx? If so, that means it's conservative. So we're going to check that. So if we calculate my, we're going to get my is equal to 4x cubed y cubed. And then nx would be the same. So f is conservative. Now for this particular vector field, you may be able to just mentally think about what would the potential function. Can anybody think of what it would be? Just kind of come up with it just off the top of their head.
I'm kind of bad with that. That's why I stayed.
Okay, great. So let's find it out. So, so there exists a potential function f such that the gradient of f is equal to f. All right, so remember that the gradient is going to be fx comma fy. Those are going to be the component functions. So this implies that fx is going to be equal to x to the third y to the fourth. And so to find our function, we just integrate with respect to x, and we think of y to the fourth as a constant. So what would be the antiderivative of x to the third?
X to the fourth divided by 4.
Yeah, so this implies that f of xy is going to be 1/4 x to the fourth y to the fourth, because that's just a constant. And then we're going to have a function of y. That's like the arbitrary constant. And then in this case, I think the arbitrary constant is going to come out to be 0, because if we have fy, so if I take the partial derivative of this guy with respect to y, what I'm going to get is I'm going to have x to the fourth y cubed plus h prime of y. And fy is going to be equal to my y component of my vector field. So it's equal to x to the fourth y cubed. So these guys are going to cancel. I can just subtract those guys. And that means that h prime of y is equal to 0. So that means that h of y is just equal to some constant c. And for simplicity, I'm just going to take c equal to 0. And so what that means is that my potential function is equal to 1/4, and then we have x to the 4th, y to the 4th. All right, so now that we have our potential function, now we can evaluate the problem pretty easily with the fundamental theorem. So we know that our vector, our curve, is given by the r of t. And so when you have a conservative vector field, it's independent of path. And so all we care about are the endpoints of the path. So we can find the endpoints of the path by just plugging in 0 and 1. And so we know that r of 0 is just going to be equal to 0, 1. So that means that one endpoint is at 0, 1. And then we calculate r of 1, and that's going to be equal to 1, 2. So we're going to use the point 1, 2. And so what we have then is that our line integral over our curve f dot dr is going to be equal to the gradient of our potential function, which was the 1/4 x to the 4th, y to the 4th. And then we just need to put the endpoints in 0, 1 and 1, 2. So we just have that. And then by the fundamental theorem, this is just going to be our potential function at the endpoints. So what we're going to have is I'll have 1/4 x to the 4th, y to the 4th, from 0 to 1, and then from 1 to 2. And so let's put in those values, see what we get. So we'll have 1/4, and then I'll have 1 to the 4th, and then 2 to the 4th, and then minus 1/4, and then I have 0 to the 4th, and 1 to the 4th. So this is going to give me 16 over 4, which is 4. And so that's it, we get 4 there. All right, so that's one review example. Any questions on this one that I just worked?
Oh, it's pretty simple.
Yeah, it's not bad at all. Let's try another one. So we're going to evaluate the surface integral. And the surface integral is going to be, we'll have y z over s ds, where s is the part of the plane z equal to y plus 3 that lies inside the cylinder. And so in this case, so we've got our cylinder. And right here, we're going to be going up here like this. And so this is so S is the part of the plane, is equal y plus 3 that lies inside the cylinder. And so in this case, this part is our S in here. So S is right in here. That's the part. And then this is going to be over this patch right here. This is D. D is right there. So that's going to be the x squared plus y squared less than or equal to 1. And in this case, this would be like your y-axis right here. That's your y. And then this would be your x right here. All right, so now you have to remember that there's two different types of surface integrals we looked at. It was like the basic surface integral, and then there was the flux integral, the vector one that had a dot product. This is a basic one. And so remember that the ds is going to be equal to the zx squared plus the zy squared plus 1 dA. So that's what the ds is there. And then once you transform it to this becomes just a regular double integral. And so now our surface, our z is equal to y plus 3. So what that means is that the zx is equal to 0 and the zy is equal to 1. And so then ds is going to be equal to, according to this formula, we're going to have 0 squared plus 1 squared plus 1 dA. And so the ds is just equal to root 2 dA. So we just have that. And so then when we look at our integral, so we have the yz ds over s. This is going to become the integral over d. And then we're going to have y. Remember that the z is equal to y plus 3. So we'll plug that in for the z. So we'll have the y plus 3. And then ds is going to be equal to root 2 dA. And so now this is just boiled down to integrating this function over this polar region. So we're back in chapter 15 doing a double integral that we can easily convert to polar. So what we have is we're going to have the root 2, and then we're going to have here y squared plus 3y dA all over d. All right, so let's convert this to polar. So in polar, we'll have the root 2. We're integrating over a unit disk. This is radius 1. So we're going from 0 to 1 and then 0 to 2 pi. And then the y squared is going to be r squared sine squared. And then we're going to have r, we're going to have 3r sine theta. And then we're going to multiply that by the r dr d theta. So that's the dA becomes r dr d theta when you convert to polar. So let's see, so we'll have the root 2, 0 to 2 pi, 0 to 1, we're going to have r to the third sine squared theta, and then plus 3 r squared sine theta, dr d theta. And so now we can go ahead and integrate this. So we're going to have root 2, 0 to 2 pi. Here we're going to have 1/4 r to the fourth sine squared theta. And this is going to be r cubed sine theta. And then we're going from 0 to 1. And so at 0, when r is 0, both of these guys are 0. So that's going to give me a 0 there. And at 1, we're just going to end up with root 2, 0 to 2 pi of 1/4 sine squared. Plus sine theta.
Wouldn't it be r cubed over 3?
No, because you have the 3 there.
Oh, right. Oops.
So it would be,
Okay, never mind. Yeah, I'd
the
cancel.
3's would cancel. And so let's finish this one. So we'll have, for the first one, we're going to have root 2, 0 to 2 pi, and this is going to give me 1/8 minus 1/8 sine, cosine of 2 theta, and then plus the sine of theta. And so now we can go ahead and integrate this. So we'll have root 2, 1/8 theta. And then in this case, we're going to have minus 1/16 sine of 2 theta. And then this one is going to be minus cosine theta from 0 to 2 pi. And so let's see what we get. So we're going to have root 2, and then we're going to have 1/8 times 2 pi minus 0 minus 1/16 times 0 minus 0, and then minus 1 times 1 minus 1. And so the only thing that's not going to end up being 0 is from this first part. So we'll end up with pi times root 2 over 4. So we have 2 pi times root 2 over 8, and we can reduce it down to just be pi times root 2 over 4. Questions on that one?
None.
Okay, I'm just going to do a couple more examples. You can hang out for that. So example 3. So we're going to use the divergence theorem. To compute the flux of F equal to 3xy squared e to the z and 3x squared z across the surface S. Where S is the surface of the solid G enclosed by the cylinder, x squared plus y squared equals 1, and the planes z equals 1 and z equals 4. So there's times when you can use the divergence theorem and there's times when you can't use the divergence theorem. So the divergence theorem can't be used on a basic surface integral. So like the one that we just did, this is a surface integral, but it's not a vector surface integral. It's not a flux integral. And so we wouldn't use the divergence theorem on this one. And also your surface has to enclose a solid. So sometimes we're calculating the flux of a vector field across a surface, but it's not a surface that encloses a solid. So to use the divergence theorem, you have to have a surface that encloses a solid. And it has to be a flux integral that you're wanting, not a basic surface integral. All right, so our surface in this case is we have the cylinder. And so here we have the z equals 4. That's the top. And then we have the z equals 1. That's this bottom. So this is not on the xy plane. And then we have the lateral surface, which is the x squared plus y squared equals 1. And so our surface consists of 3 parts. So we have this lateral surface, this top surface, and this bottom surface. And so if we had to do this normally, without the divergence theorem, we would have to calculate 3 separate surface integrals. But with the divergence theorem, we only have to calculate 1 triple integral. And so what the divergence theorem says is that the flux integral f dot n ds, which normally we would have to split up into 3 different integrals. We'd have to do an integral over S1, an integral over S2, an integral over S3, and then add them up, that this is just equal to the triple integral over G of the divergence of F dV, where in this case, G is our solid. So this S1, that's the surface. So this one is the surface. And then G is the solid that's enclosed by all these surfaces. All right, well, we need to calculate this divergence. So let's go ahead and calculate that divergence. So we need, remember, to calculate the divergence of a vector field, you take the partial derivative of the x component function with respect to x. So that's going to give me 3y squared. And then we take the partial derivative of the y component function with respect to y. That's going to give me 0 because I have e to the z here. I have plus 0. And then the partial derivative of the z component function with respect to z is 3x squared. And so what I end up with here is a super nice one for cylindrical coordinates. So this is going to be just 3x squared plus y squared, 3 times that quantity. And then we're going to have dv over g. And so we can evaluate this pretty easily just using cylindrical. So in cylindrical, what you're going to have is this is going to end up being 3r squared. And then you're going to have times r and then dz, dr, d theta. So remember, the cylindrical is kind of like polar, only you're letting the z just be z, and then everything else is like polar. And so the z is going to go from 1 up to 4. And then it's a unit disk down here. So we're integrating over a unit disk. So that disk would be just like right down there that you're integrating over it. This is z equals 1 is right here. And then this is like your d that you're integrating over down here, like your projection of it. And so then the R is going to go from 0 to 1, and this goes from 0 to 2 pi. And so we can easily split this up into a product of things. So here we're going to have, this is going to be 3r cubed. So we're going to have the integral from 0 to 2 pi of just 1 d theta times the integral of 3r cubed from 0 to 1, and then times the integral from 1 to 4 of just 1 dz. And so this one is just going to be 2 pi, and this is 3. So we're going to have 2 pi. This one is going to be 3/4 r to the 4th from 0 to 1, and this one is 3. So we'll have 6 pi, and this one is going to be times the 3/4. And so we're going to have 9 pi over 2 once we reduce it. So we're going to have 18 pi over 4, and that's equal to 9 pi over 2. And so that would be the flux. So you could think of it as like a mass flow rate out of the surface of the solid. So 9 pi over 2. I'm going to just take a look at one more. And so we're going to use Stoke's theorem. To evaluate the line integral over C of f dot dr when f is equal to x minus y and then x squared plus y squared. And C is the boundary of the surface z equal to 4 minus x squared minus y squared, z greater than or equal to 0 in the xy plane. We assume that n is in the positive z direction. And so if you remember, that's going to induce a counterclockwise orientation on the boundary curve. So we have our surface is like this. And so this is our paraboloid. And then here you have your boundary curve. And because the normal points up, that means that you have to have a counterclockwise orientation along the boundary curve, because as you walk along, your head has to point in the same direction as the normal in that case. All right, so in order to calculate this line integral using Stoke's theorem, we have to calculate the surface integral using the curl. And so if we look at the curl of f, remember that that's equal to the del operator crossed with f. And so we're going to have the I, the j, and the k. And then we have these partial derivatives. Hope you're starting to get the hang of this now. And then we have the component functions, the x, the minus y, and the x squared plus y squared. And so when we do this, we're going to have 2y minus 0. And then we're going to have 0 minus 2x. And then we're going to have 0 minus 0. So the last one is going to be 0. And then if we look at our n, so we're going to remember that n is going to be equal to minus the zx minus zy and then 1 divided by its magnitude. But remember that the magnitude part cancels out. And so in this case, what we're really interested in is we're going to have our surfaces here. So the minus zx is going to be minus a minus 2x. So this is going to be equal to 2x. And then we're going to have 2y. And then we're going to have the 1 divided by that magnitude part, which is going to cancel anyway. All right, so then if we look at our line integral, so this is going to be our curl of f dotted with n times the ds over s. And so what we're going to end up with is we're going to have this. So we're going to have the curl was the 2y, and then the minus 2x and the 0. And then we're going to be dotting this with 2x, 2y, and 1 dA over d, where this is our d here. And so what you end up with is you can have a 4xy minus 4xy and then plus 0. And so we're just integrating 0. Which is equal to 0. And so in this case, we get an answer of 0. It's not because this was a conservative vector field. Was it a conservative vector field though? Did this vector field turn out to be a conservative vector field here? How do we know that it's
Doesn't seem like it.
It's not, because if it had been a conservative vector field, then the curl would have been the 0 vector.
Yeah.
So because the curl was not the 0 vector, it wasn't a conservative vector field. So it wasn't equal to 0 because we were integrating a conservative vector field around the closed curve. It wasn't that, it just turned out to be 0 in this case. All right, so I'm actually going to do just one more. Give you guys a nice review of some of these topics that we've been looking at. So this is going to be the last example though. So example 5. And so we're going to evaluate the flux integral to determine the flux of F equal to, we're going to have the X Z e to the Y minus X Z e to the Y, going to be the second component, and then Z across the surface of the plane of the part of the plane X plus Y plus Z equal to 1 that lies in the first octant. Right, so whenever we're doing calculating flux, we always like to use the divergence theorem if possible. In this case, can we use the divergence theorem?
Is it enclosed?
It's a plane. Is a plane
Oh,
enclosed?
okay. No.
So that means that we cannot use the divergence theorem.
Yeah.
Since our surface is a plane and it doesn't enclose a solid, we can't use the divergence theorem. So let's make a note of that. So since the surface is a plane that does not enclose a solid, this implies we can't use the divergence theorem. So that's okay. So then we're just going to have to calculate So we're going to calculate this guy. So we're going to have to calculate F dot N ds, where the N is going to be equal to minus Zx minus Zy 1 divided by the square root of Zx squared plus Zy squared plus 1. And then the ds is going to be equal to the Zx squared and then the Zy squared plus 1 dA. So when I multiply these two together, the square root parts cancel, and I'm just going to have this numerator part dotted on with the vector field. All right, so in this case, the Z, if we look at our plane, if we solve it for Z, we're going to have Z is equal to 1 minus X minus Y. And that means that the Zx would be minus 1 and the Zy would be minus 1. And so we're going to have the minus Zx and minus Zy, 1 is going to be equal to 1, 1, 1. And this is nice, it points up. So in this case, if we look at our surface, so we have this plane. So this is going to be Z equal to 1 minus X minus Y. And we're orientating the normal so that it points up. So in this case, our normal is going to be kind of coming right out of there like that. And so the normal is coming out. And so it's pointing up. And so what we also need to do is we need to calculate this region, because we're going to be integrating over the region. This is going to be a region D. And so in this case, when Z is equal to 0, we're going to get Y is equal to 1 minus X. So here we're going to have Y is equal to 1 minus X. And this is going to be 1, and this is going to be 0. So we're going to end up integrating over this nice type 1 region here. All right, so let's see what we have here. So we're going to have all right, so we're going to have our double integral of f dot n ds is going to be equal to, so we have a surface integral here. So we're going to have our vector field, which is going to be the x, z, e to the y, and then minus x, z, e to the y, and then z, and we're going to dot this with 1, 1, 1 over root 3, and we're going to times it by root 3 dA, and we're going to be integrating over the d, and then these guys cancel. I don't know why I keep on writing that. I could just skip that step. Now, one thing to keep in mind is that the z is equal to 1 minus x minus y. So I could have put that in here, but I didn't want it to be too huge when I did it. So after I simplify this, then I'll go ahead and put in the z. So when I do the dot product, it's going to simplify, because I'm going to have an x, z, e to the y, minus x, z, e to the y, and then I get the z, dA. And so these guys just cancel out. And so I'm just integrating over z. And remember that the z is equal to 1 minus x minus y. So I'll go ahead and put that in now. And now I'm just doing this nice double integral. So now I'm back in chapter 15, and I'm integrating this nice double integral over this nice type 1 region here. And so we can integrate this. So since it's a type 1, that means I'm going to integrate dy and then dx. And so we're going to go from 0 to 1 minus x. And then the x goes from 0 to 1. So we have this nice type region. So we're integrating it. So we're thinking about integrating it like this. All right, so we're almost there. So now let's see what we have here. So we're integrating with respect to y. So we'll have the integral from 0 to 1. We're going to have the 1 minus x times y, and then minus 1/2 y squared. And we're going to go from 0 to 1 minus x. Everything's going to be 0 at the lower limit. And so when we put in the 1 minus x, we'll have the integral from 0 to 1. I'm going to have 1 minus x squared minus 1/2 of 1 minus x squared. And so we end up with 1/2 the integral from 0 to 1 of 1 minus x squared, which we can flip around since it's squared and just write it as x minus 1 squared. And so that will just give me 1/6 x minus 1 cubed. And so I end up with 1/6.
It's literally frozen. Yeah.
It's frozen?
It's still frozen.
How about now?
I think we got it.
Is it still frozen?
No, it's good now.
All right, so then we're going to have, from my end, it didn't look like it was frozen. It looked like it was moving. Sometimes it's like that. So we're going to have a 1 minus 1 cubed, and then minus a 0 minus 1 cubed. And so we just end up with 1/6 and 0 minus a minus 1. And so we get 1/6. And so the upward flux across S is 1/6. And that's it for today. I hope you guys have a good day.